So yeah, I have started the recording. Yeah. So yeah. So last time we discussed asymptotics of functions. In particular, we focused on the order notation, the big O notation, and yeah, I think that there are a couple of things that maybe we'll talk about before getting into the technical part. So some of you had requested to change the timings of the tutorial, right? And so I have created a Google form where you can select your slots, whatever whatever suits you. So the link I've put in. So unfortunately, the Swayam portal, I couldn't get hold of the portal to put a poll there. So what I've done is there's a Google Drive that has been shared with all of you where you can find the links to the recorded lectures, and you can find the notes, these notes that are uploaded. So were you able to access that? You could maybe use the chat box and okay. So thanks. So in the notes that have been uploaded, I've pasted a link to the Google form, where you can submit um, your preferences. So I'll just, I've also put it here again, so you can maybe uh, try to give uh, okay. So this is the Google form for tutorial timings, and there are only few slots that they have given. So there's not much freedom there, but there are couple of options. So you can do maybe the votes by maybe by Monday midnight, and then we'll look at the majority, whatever works best for most people. And I can't promise that it that that I mean this will we can reschedule it, because I need to take permission from the authorities who are handling it. So if they are okay with changing the timings and rescheduling stuff, so that would be fine by me. But yeah, I'll keep you posted. mm, yeah, and if there is a change, then you will get to know through mails that you are usually getting the reminders about the tutorial. So yeah, so you'll get the announcements there. And yeah, so is that fine? Okay. um yeah, so that's about that. And I'll also paste the link here in the chat in case you can't access it. So I just put it here. And yeah, that's all. Okay, so yeah, the other thing is, I mean, I'd announced this last time also, but for those who came for the first time today, if you have any queries regarding the questions or assignments, you can email me at okay. And the books that we have for the references that you have for this course are the standard references for algorithms course. One is CLRS, or you can call it Corman, Lysers, and other authors. So if you just write that, you'll find the book on algorithms. And the second is by Kleinberg Tardosh. The name of the book is Algorithm Design, I think. Okay, so there are a lot of practice problems in both the books, and some of them are solved, some of them are not solved, but all of them are interesting. So if you're looking for problems of any kind, then this is a good reference to take a look at. So yeah, that is all about the logistical part. And yeah, so we can start with the technical part, unless there are any questions. um, Sorry. In quiz there's a term h of n. mm, okay, I'll maybe check the question once, so let me do that now. Oh, h of n is just any other function. So like f, g and so on, h is just any other function. So uh, I mean, does that answer, or do you have any further question? Okay, it's um okay, it's something like saying that, let's say you have two numbers, say 4 and 10, and now you have an unknown number, let's say x. So then you don't know the value of x, but you can still make some claim about x, right? It can't be that x is smaller than 4 uh, but larger than 10. That cannot be. So it's something like that. So you have f and g as two given functions, and you can compare which is larger using the idea of asymptotics, and h is something that is not known to you, but you can still say something about it using the fact about f and g. So is that fine, or do you have further question? Okay, okay, good. Okay, any other thing before we start with the
उसी में
I could not hear you. Can you repeat? Okay, I don't know what is the question. So can you paste it in the chat box? No, it's not. Yeah. So no, I don't think there's anything difficult about it. I think it's on the easier side. So there are some questions that would be easy. But is there anything in particular that you think is vague, or okay? Yeah, yeah. Okay. 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 So let's get started. So the topic for today is
आपके पास
searching
यूपीआईडी
and
का नंबर है आप
uh, did anybody speak up right now? I couldn't hear. Sorry, can you please repeat? Okay. Okay. So the topic for today is searching and sorting algorithms. And also, last time a couple of you had mentioned that some of you don't have the background, discrete math background or maths background. So if at any point you feel like there's something that you don't understand and you would like me to explain further, then don't hesitate. Okay. So okay. So um yeah. Okay, so what I'll do is I'll just get started with the questions, and whenever it's needed to recall something, we'll get there. So what I'll do is I'll just give you a problem. um yeah. So I'll just give you a problem, and it's just I mean, it's an algorithmic question. So what you have to do is you have to come up with an algorithm for solving the problem. So the problem is as follows. Um, so um, okay, so you okay, you are at a pancake house, and there are lots of pancakes that are there, but all of them are of different sizes, and they're arranged like one on top of the other. So assume this is a pancake, and then there's another on top of it, there's another on top of it, and they're all of different sizes, and they're arranged randomly. So what you have to do is you want to sort them in the ascending order of size. So let's say I want the smallest to be on the top, then the next largest, then the next largest, and so on. So at the end of the day, I want my pancakes to be sorted nicely. So the problem is that you're only allowed to flip it. So what you can do is you have a spatula, and let's say you can keep it here, and the only operation that you can do is you can flip whatever is there above the spatula will get flipped entirely. So okay, so what will happen is, let me just number these. So right now this is the first smallest, the second smallest, third and fourth. Okay, so I've just written a number based on their sizes. What happens when I put my spatula here is the pancakes on the top will get flipped. So what will happen? So what will come on the top now? What is the order of the uh, pancakes now? Yeah, you'll have one on top, then yeah, then you'll have four, and then you'll have three. Yeah, you have one, four, then three, and then two. Okay, so what I want at the end of the day is I want it 1, 2, 3, 4, like that. And assume that you have n many pancakes or k pancakes. So there is a stack of k pancakes here in some order. I don't know what the order is, but there are k of them. And what I want is I want them in this order. And the only operation that you're allowed to do is flip. You can flip as many times as you want, but yeah, but you want to, at the end of the day, you want to minimize the number of flips. So the question is, how will you do this so that the number of flips is minimized? So you can come up with the best algorithm that you can. So you don't have to code it right now. You can just tell me the idea or pseudocode, or yeah, that would be fine. Okay. Okay, so you think about it for maybe 5 minutes. In the meantime, I'll address the questions in the chat. Okay, I'll show you the question. Yeah, you can read it here. Okay. Okay, if you think you have ideas or answers, you can write in the chat. I am looking at it. I'll maybe comment on it. Um, okay, okay. Okay, so if you have an algorithm, in the meantime, you can also try to come up with the running time that your algorithm takes. Okay, so for those of you who are thinking of trying to use, like, say, bubble sort, quick sort, or something, uh, think of the operations that you are allowed to make. So you are only allowed to flip, right? In the bubble sort, what you do is you can access any random I mean, any two consecutive pancakes and compare amongst them. But I mean, in bubble sort, for example, you flip between the consecutive um, elements, right? But the flipping operation does not allow you to do that. It only allows you to insert somewhere and flip the entire thing. So is that making, and the same thing will happen for any standard sorting algorithm that you might have seen, like quick sort, mud sort, or anything. Like the difference here is in the data structure that you're using. There you have an array which allows you to make all these nice operations. You can compare any two elements and do swappings and stuff. But the problem here is you're only allowed to um,
And
yeah.
in the question it says you have to find using minimum number of flips. So the algorithm complexity doesn't matter, right? If I mean it could
Yeah,
be a
in by
long algorithm, but it takes minimum number of like
yeah,
flips.
by algorithm complexity we mean generally we mean running time, right? But in this case, assume that flip is the only operation you are doing, no? So
Okay.
yeah, so number of flips would give you the time. I mean,
Okay.
yeah.
I mean the naive idea is that find the smallest and then bring it to the top, then the second smallest and then bring it to the top. That is the naive idea. I don't know if there's any better
Okay, so
solution.
yeah, that is correct. So in fact, in what you're doing sorting in the reverse order, I think, because at the end what you'll get is you'll get one at the bottom, no? So in your case what will happen is that the largest one will come on the top, then you can flip one more time and get the whole thing reversed. But yeah, I think the idea is correct. And for those who are thinking along the lines of, say, quick sort or bubble sort, is it clear why it will not work? Is does the comment address the problem, or do you have okay, if so we'll discuss the solution. I think what Suyog, Anish, and uh, yeah, sorry, I'm Tanvi. Yeah, I think the idea that you are all thinking is on the correct lines. So we will discuss that solution. We will analyze its complexity. I mean the number of flips that you need, and then if you have any questions based on your ideas, we can take it up. So yeah, so like you said, the idea is simple. You'll do the most natural thing that you can think of. So what okay, let's say I'm just taking a random example, maybe 4. You have 4 3 4 5 1 3 2. So these are the sizes of the pancakes, although I'm not drawing them, but these are the pancakes. This is the input that is given to you. And the idea is that um you put your spatula on the uh, yeah, you put your spatula on the largest sized pancake, and you flip it. So what you'll get is you get 5 4 1 3 2. Is this fine with everyone? Okay, so then what we'll do is we have we have the largest one on the top. Now what we'll do is we'll find the next largest one, which is 4. So now I'll put the spatula at 4, and now we will flip the whole thing. So what you get is you get 4 5 1 3 2. Okay, wait. Okay, maybe what I'll do is sorry, I'll reshuffle the whole thing. Sorry. So I want this 5 to go to the bottom. So what I'll do is I'll flip this. The next time I'll flip at 2. So what you get is 2 3 1 4 5. So now the fifth one is at the bottom, and you can assume that this part is sorted, and now I just want to sort this part. So where do we put the next spatula? I mean the spatula next on 4. But should we do that because 4 is already on the correct place, right?
Yeah, on 3 then.
On 3. So now you put a spatula here. So what do you get?
3, 2, 1, 4.
3, 2, 1, 4, 5. And then next where?
Now you put it on 1.
Now you put it on 1. So that 3 comes at its correct place. So what do you get? 1, sorry, yeah, you get 1, 2, 3, 4, 5, and now you have the whole thing sorted. So there are a couple of different ways in which you can do it. There are small variants of this, but eventually the idea is the same. You are sort of um, yeah, I mean, you're sort of trying to get one item right in its correct place, then trying to solve for the smaller problem again and again, one at a time. So uh, yeah, so how do we know that the element is at its, I didn't understand. Are you saying I didn't understand, what do you mean by how do we know the element as is at its right place?
I mean, because we are checking for the next biggest, right?
Yeah,
So
so
it
okay,
automatically takes care of its place. That's
yeah,
what I'm
so
saying. If we place it on the, like it's the next largest, so the above one should be the next largest one. That takes care of the place. I think that
that
is
takes
what he
care of the
means. I
that
think
takes care,
that takes care of the place. Sorry.
okay.
Like I mean, he want. I think the doubt was that how do we know 4 is at its place?
Oh, okay. So this is unlike career. You don't have to specifically go and see what the values. It's a. I mean, um, it's a set of pancakes that given to you, so you can see the sizes clearly. So you don't need to query to find the value of the. I mean, the size of the pancake. You can see it directly. It's given to you. Okay. Okay. Good. So okay. So maybe I'll write the algorithm a little. I'll try to write a pseudocode. But before that, if the algorithm is clear, what do you think is like the number of flips that our algorithm takes in the worst input possible?
मुंडे बोला कि दवा है ये नहीं यार
I think I don't know, but I think 2n.
Yeah, yeah, that is correct. Um, so what we are doing is okay. So I'll just write a pseudocode that you find the max sized pancake which is still not in its correct place, and then you flip, okay, maybe like then put spatula below it and flip, and what will happen is now this pancake comes to the top, and what we'll do is yeah, place your spatula above the desired or correct position and flip, and then you repeat this. Okay, so what happens is in maximum 2 flips you will get the largest pancake at its correct position. So in this case 5 was not in its correct position, so we flipped it once to get it at the top and then flipped it once to get it at the bottom. So in 2 flips 5 is in its correct position, and now you have to solve the same problem for the rest of it assuming that 5 is in its correct position. So for every element you are spending 2 flips at maximum, so there are k many pancakes, so that would take you 2k many flips. Okay, so what is the complexity of algorithm in terms of number of flips? So we're saying that there are k pancakes, each so overall it will be at most 2k many flips. So yeah, okay. Okay, so if so in the comments you're saying that so by descending order you mean that everything is like 5 4 3 2 1, is that what you mean? Yeah, if that is the case, then you are just going to do it in one flip, no? If you just flip it once at the bottom, then uh, it will be sorted entirely. Is that clear? Okay, okay, good. And you can try to see what is the worst kind of input instance that you can create. So that's something you can think about. So you can try this out. Find the worst case input instance for our algorithm. Okay, and yeah, so that is one thing. Now that we have this algorithm, can you try to write a recurrence relation for this? So what I mean by that, so are you aware of recurrence relations, or um,
Yes.
okay, so can you try to come up with a recurrence relation for our algorithm?
Just before that, for this question, the worst case is if the input is like a Christmas tree, would that be the worst case? Like a triangle on a triangle on a triangle sort of structure? Then for our algorithm, it will be the worst case, I think.
Yeah, I mean I didn't try it out, but it looks like that might be a worst case example to me. um okay, okay, so can you try this recurrence thing? Okay, what we mean by recurrence is let's say that t of n is the, let me just define that. So let's say t of n is the number of flips required to sort k pancakes, then k pancakes for the given input instance, then can you write t of k, for example, in terms of say t of k minus 1, t of k minus 2 or something? So basically in terms of smaller input, if that makes sense. Otherwise we can skip it, it's not necessary. So I mean, if you're not aware of this, that's also, you can let me know, we can skip this part.
I mean, it will be like 2 plus t of k minus 1, right?
Exactly, it will be 2 plus t of k minus 1. So why is that? Because you want to sort the whole set of k pancakes. What you're doing to do that is you're finding the maximum one, putting it on the top, then you're again flipping it and putting it on the bottom. So that takes 2 flips at most for the maximum sized pancake, and then your job is just to sort the remaining k minus 1 pancakes on top of that. So it's like you have solved a problem, a smaller part of the problem, and converted it into another problem but with a smaller size. So yeah, if that makes sense, then it's okay. Otherwise, if it does not, it's still fine. But you can try substituting here. You can use the substitution method or anything, and try to solve this, and you'll end up getting uh, you'll end up getting something like 2k. So yeah. Okay, so although it's not the same as the, like, say, quick sort or merge sort or anything, that any of the sorting algorithms that you might have looked at, but the idea is borrowed from uh, one of the algorithms that you have seen. So can you see which sorting algorithm that you've seen is similar to this? Although the implementation wise it's different, but the idea is the same. The way.
Insertion sort, I think.
Mm,
Or no, am I wrong?
is it insertion or is it selection? Because what selection does is it takes the minimum element and places it in its correct place, then tries to solve the rest of the array. So
Okay, yeah.
yeah, that's what selection does, and what insertion does it is it tries to build the solution part by part, taking one element extra at a time. So I think somebody had also written in the comments earlier that you can use something like a selection sort. So that's indeed a correct intuition, but the running time of selection sort is order n square. Here it's order n, and that's because the operations that you're using are different. Okay, and yeah, so for those of you who are curious, I think we last time we asked this thing that you have a problem and you try to come up with an algorithm for it, and you analyze its running time. That's something you do, but then the next important question that you want to know is it the best possible, or is it possible that somebody comes up with an algorithm that's better than this? So maybe it runs in order square root n time or log n time or something. So that's something we are interested in, and that's the lower bounds that we're talking about. So how do you show that you cannot do better than something, and all that stuff? So this problem is so the problem that we defined today, it's called pancake sorting problem, and it's a very well studied problem. And what we saw is just now is a trivial order and solution. um, yeah, so what we saw just now is a trivial order and solution, but there are better bounds than this. One of the bounds is due to Bill Gates and Papa Dimitriou, and they've done something. It's definitely little of n, but I don't exactly remember the. You can search it out later on. You'll find a lot of articles about this, but the lower bound that we have is also not very good. I think it's something like logarithmic, although I don't exactly remember. So there's a huge gap between the upper bound and the lower bound that is there. So you can so it's a open problem to improve the say number of flips or running time, let's say. Okay, so it's if none of this makes sense, that's also fine, but for those of you who are interested in looking at it further, I'm just giving references. You can take a look at it later. So other than that, is the algorithm and the analysis of running time clear, or are there any questions? Then please let me know.
Hello.
Mm-hmm.
Could you please explain again, like how did we reach to the recurrence relation? That this will be the relation.
Okay, okay. So what we did is we have this instance that we want to solve. This is the t of k for us. And to do that, what our algorithm does is it finds the largest pancake, puts it on the top. So that took us one flip. And now the correct position that it should be is in the bottom, because we want to sort it in the ascending order. So then we'll put our spatula here again and flip the whole thing. So this is what you get. So in two steps or in two flips, you got the largest element at its correct place. So that's why in order to solve the whole problem, you are using maximum of two flips to solve for one pancake, and then your job is just to sort this thing uh, as 1 2 3 4. So you can think of this as a smaller instance of the problem where you have k minus 1 input size or k minus 1 pancakes. So that is your t of k minus 1. Okay, good, good. So yeah, so Abhinav has a question that sorting has a lower bound of n log n. So how do we implement this as order n? So like I said earlier, this is not an array data structure. So the data structure and the operations that we are dealing with are entirely different, and that's why you have different bounds. And the other thing is the n log n bound only holds for comparison based sorts. For there could be some very different sorting algorithms that do something other than comparison. So um, yeah, so the whole idea is that you have a different data structure and different operations. So does that make sense?
Ma'am, I think even in this, algorithmically, it will be O of n square because we have to find the second largest every time.
Yeah, so that's what I'm saying, that the pancakes, you can see the pancakes. You don't have to query and see which is the larger pancake, right? If I put different size pancakes in front of you, you can directly see which is the largest one, right?
Right, right.
So yeah, so that's how you are saving on the time or flips or whatever. Okay, good. So other than that, are there any further questions? Okay, and somebody was asking the link for the previous recording. So all of these are going to be accessible through the Swayam portal, but I'll just share you the link of um, okay, so I've shared you the link for playlist. So this is so all the recordings of tutorials are going to be uploaded here, and you can access it directly from here, or you can also check it on the Swayam portal. Anything would be fine. Okay, so let's move on to the next question. Okay, so okay, so now you already know how to sort the pancakes. So what I'm giving you is already a sorted set of pancakes. Okay, but one of the pancake is different. It has a special syrup added to it. So maybe let's say it's this one, and you want to find that one. You want to locate it. Okay, locate it in the sense you want to bring it at the top. Okay, of course you can um, okay. Okay, maybe let me put it better. So hmm, okay, okay, so maybe I'll explain this again. So in this case, the setup that you have is slightly different. So what happens is you have this set of pancakes that are sorted in ascending order. One of them is special, you want to find it, but uh, the difference here from the previous cases, in the previous case you could see them, you could explicitly see the pancake and find out. So if I were in the previous setting, what I would do is I'll just put my spatula here, flip the whole thing, and get my golden syrup pancake at the top. But now the difficulty I have is I'm not allowed to see the pancake. So this is something that is hidden from me, and there's somebody at the back who is going to tell me. So I'll just blindly put my spatula somewhere, of course in a correct, I mean in a valid position. So let's say I put my spatula here, then then the person behind, so I'm here, let's say I can't see this, but I can put my spatula, and the person behind will tell me whether the spatula I am interested in is larger or smaller than the uh, golden syrup pancake. So that's the only thing I know. And now, just using this, can you come up with an algorithm to bring this hidden golden pancake at the top, and always assume that this person is going to tell you the correct answer, so there's no fishy thing going on here. Yeah, they're always going to tell you the correct answer whenever you ask for a pancake. They'll tell you whether it's larger or smaller than the golden pancake, so you'll always trust their answers. So the question is, so you want to minimize the number of comparisons to get the pancake at the top. So yeah, maybe try this out for a couple of minutes. Okay, so I think, yeah, most of you got the correct idea. So the idea is that you do something like a binary search, and what would be like the running time complexity of that? Okay, it would be order login. Yeah. Okay, so I'll just I think all of you got this correctly, but I'll just iterate the algorithm. So the algorithm is going to be that um, you will, so maybe I'll take an input instance and run our example on that. So let's say you have this sorted array, and let's say that 2 is the golden colored pancake and I want to find it. So what we'll do is we'll use our binary search idea. We put our spatula in the middle, which is 4 in this case, and we ask whether 4 is greater than 2 or smaller than 2. So it so happens that 4 is larger, so that means my answer should lie in somewhere here. It can't be here, because the golden spatula, the golden pancake is smaller than that. So now we have reduced our search space to this part, and we do the same thing again. You ask the middle element, so the middle element here is 2, and you ask whether 2 is smaller, larger, or equal to 2, and it will tell you that it's equal, and then you would have found your golden pancake. So so it's the same idea. I'll just call this subtray. By subtray, I just mean that this is what your tray contains initially. Then as you keep on dividing and conquering, you sort of reduce your size of tray. So I'll just use that term, although it's not, I mean, you can use any other term. So, and yeah, so if the middle pancake is equal to the size of the yellow or golden, I'll just call it G, which is the golden pancake size. Yeah, then you already have your answer. Then done. So yeah, anybody would like to complete this? So else if it's larger, then what do you do?
We have to put the end to the, I mean, before middle.
Yeah, you continue from say top to middle minus 1. That's your sub problem now. And else what you do is else what do you do?
Our bottom to middle plus 1.
Yeah, you continue from middle plus 1 to um, end, whatever that is. Okay, so and the analysis is almost, yeah, is exactly the same as that of binary search, so we'll not analyze it, but you can maybe just tell the recurrence relation. um, so what would be the recurrence relation for our algorithm?
Ma'am, I'm not sure, but I can tell that it should be 10, I mean, t of n by 2 plus 1.
Yeah, plus 1 or some constant, yeah. So yeah, that's exactly correct. So what you're doing is you are just dividing your sub problem into half part, I mean half the size every time in constant operations, which is the comparison in this case. So yeah, that is correct. So are there any questions regarding this? um, okay, so then we'll move on to the next question. Okay, so sorry, there is a query. So why do you think it will not be t of n over 2? Because what we are doing is you ask at the middle, and if it is larger, the middle one is larger, then you only check on the top sub subset. And if it is smaller, so let's say the golden pancake was somewhere here, then you would only ask your queries on this other half, maybe not even 4, on this other half. So that is what you keep on doing every time, right? You are discarding half of the space. So does that clarify? Oh, sorry, okay, sorry, I meant t of n over 2. Yeah, thanks for pointing that out. Sorry, I did not realize I missed through, I mean, yeah. Okay, so now is it uh, okay, okay, thanks for pointing out. Okay, so we'll move on to the next question. So okay, maybe you read this out first, and then I'll explain what the question is. Okay. So, those of you who have like got the problem, you can try solving it. I'll just explain the question once. So, okay. So there's some Johnson packaging company, and they have designed their uh, glass jars. And so yeah, so let's say they have designed their glass jars, and they want to test how um, strong it is. So what you do is you have a ladder, and it has, say, n many rungs. um, yeah, so let's say this is height 1, height 2, and all the way up to n. Okay. So what will happen is, if you drop it, let's say you stand here and you drop it, so maybe the glass will break, maybe it won't. But then what that means is, it might break somewhere from the top. Or it can also happen that you threw it from here, it broke, then you want to find the smallest height from which it will break. So it's possible maybe it started breaking from here. So you want to find the minimum height, uh, from which if you drop, it's sure that it will break. Okay. So so what is the best running time that you can come up with? Okay, binary search. Yeah.
Ma'am, this is like a bottom to top, right? We have to keep doubling it.
Doubling.
Is that, I mean, if we try it from the second floor, then we go to the fourth floor, then eighth floor. Is that the idea?
mm, but then you will have to do it, and I mean, so you are saying you do it 2, 4, 8, 16, and so on.
Yeah, yeah.
um okay, so then you are already doing it log n many levels. So hmm yeah, but then let's say it does not break. So you're saying we do it at 2, sorry, you're saying we do it at 2, 4, 8, 16, 32, and then the end, the last one is, let's say, n, then the one that was before it would be n over 2. So let's say it did not break at n over 2, but it broke at n. That means the correct answer lies somewhere in between n over 2 and n. So um,
Yeah,
then
we have to check again.
yeah, then you have to check again. And the size here, so initially your ladder size was n, it's only n over 2, I mean it's n over 2 now, so it's not much, like it's not asymptotically smaller, so you're sort of still in the same size. So there are some ideas about binary search. So would one of you like to explain the idea further?
Ma'am, first we can check at the middle. If we just throw the jug from the middle, and if it is broken, then have to search again half of that particular length of this particular range, and in this way we can exactly find to the in which particular range it will be broken or not. Simple as the peak of the mountain problem and lead code.
Yeah, yeah, exactly. So that is correct. So what he's saying is that you use the same idea of binary search. You put it, you throw it from the middle. So let's say you throw it at n over 2 and see whether it breaks. If it breaks, then that means your correct answer lies somewhere between n over 2 and 1. So you will only now solve for this. If it does not break at n over 2, then your correct answer lies between n over 2 to n, and then you repeat the same idea. So if it's here, then you go to n over 4, drop it there, and check whether it's above it or below it, and then keep on doing that. So is that, does that make sense? Is it clear to everyone? Okay, good. So the idea is again binary search. So maybe I'll not write the algorithm this time because it's very similar to what we did so far. But yeah, you should try writing it once. Okay, and then again the running time of this would again be order login. Okay, so now the question is, how many what is in the worst case, how many jars would you have broken? Yeah, I'm coming to that. So let's only so sorry, for now I'm only talking about the part A. Okay, so in the part A, in this binary search algorithm, how many jars did we break? Yeah. Okay, in the worst case, we would have used login many jars. Okay, so is this fine with everyone? Are we good so far? Okay, good. So now the so sorry. Okay, so now let's move to the part B. So what we're saying is okay, so generally what happens in computer science is there is always, so there's something called resources could be time, um, or space, and there are many other that we'll not talk about. But by time we mean the running time that your algorithm takes to give you output, and by space we mean the space in your disk and so on that the computer uses. So typically what happens is, if I give you more time, or let's say if I give you more space, then maybe you can come up with a faster algorithm, because there is a lot more information that you can store, retrieve, and then try to come up with a clever algorithm. But if I give you less space, maybe it takes more time, or because you can't do something clever. So there's always like a time space trade-off. If I give you more space, then you can do better on time, and if I give you more time, then maybe you can do with less space. So there's always this trade-off that's happening, and in this case the trade-off that's happening is between the jars, the number of jars. This is the resource for us, because maybe we have limited jars. So the number of jars is one resource, and the other resource is the time that we are spending to find the correct answer. So what we said earlier is, I want to optimize on time. So the best that I could do was order login time. So the number of jars was not an issue then, so I was okay with giving you login many jars. But now let's say I have very limited jars, I only have one. Okay, so you can't break it before getting the answer. If you break it before getting the answer, then you're doomed. So um, yeah, so if so here on one hand we were trying to optimize on time, and this is the number of jars you needed. Now what we want is, we want to optimize on the number of jars and see how bad the algorithm will yeah, how badly will it perform. So yeah, can you think of, it's again very simple idea.
It's order n, right?
It's order n. So what is the idea?
We have to go every step. We have to go for every step.
Starting from, so where
Starting
do you
from 1.
exactly, so you can't, yeah, you can't start from the top, because if it breaks there, then you can't do anything. So you have to start from yeah, so you're going to start from 1. So okay, so what is the idea? Here's your ladder, and these are your steps all the way up to n. So what you do is, yeah, you start here at 1 and you throw the jar. If it breaks, then your answer is, you already have your answer. If it does not break, then maybe your answer lies somewhere here. Okay, so then what you do is, you throw it at 2. If it breaks, then you have your answer, otherwise the correct answer is somewhere here. So you just linearly keep on doing that, start at 1, 2, 3, and so on. And let's say it um, yeah, it breaks at k, then that would be your answer. So starting from 1, um, throw the jar and keep moving upward. Okay, and let's say at position k the jar breaks, then output k. Okay, so what is the running time of this?
Order of n.
Yeah, exactly, that is order of n, because in the worst case maybe the correct answer is n, and you would end up going all the way 1 to n. So the worst case would be order n. So now the natural question that you might have already guessed is, what we did is that we looked at the two extreme ends of the spectrum. So on this hand we are trying to optimize on the time, so we got to order log n, but we ended up spending like log n many jars. On this end we are trying to minimize on the number of jars, so here you got to order in time, but ended up using only one jar. So the natural question that arises is, what if I have say 2 jars or 3 jars, and all the way what happens for all the numbers in between? Can you do asymptotically better than uh, order n? So what I mean by that is, if I give you 2 jars, okay, then I want you to come up with an algorithm whose running time is better than order n, and that does not mean n over 2 or n over 3 or something. We mean something that is much better than n, by than order n. So for example, okay, so if f of n is your answer, f of n over n, limit n tends to infinity, should give you a 0. This is what we mean. If you put n over 2 for example here, then what will happen is this does not go to infinity, right? So this is not asymptotically better. Whereas if I put log n here, then you can see that this quantity will become eventually 0. So that's what we mean by coming up with an asymptotically better function. So is this
Now,
clear?
ma'am, I have an idea.
Mm-hmm.
Like we can take log of n, like the first step should be log of n, like log base 2 of n. If it does not break, well, then we take another step of log of 2 log 2 of n. And then if it breaks, then we have to take at max log of n steps.
Yeah. So you are using a combination of both the ideas. You're using binary plus linear.
I mean, it's not binary. How is it binary?
Not binary in the sense that you're dividing into two, but binary in the sense that you're sort of doing log n many levels instead of 2 levels.
Yeah.
Yeah. So yeah. So I mean, basically the idea of dividing into sub problems and then doing a linear search.
But I don't know if it's the there could be a better, like I am dividing it into log n, there could be some better division.
Yeah. So uh, yeah. So let's see whether that is the optimal one. So
Ma'am, I didn't get his point, ma'am.
yeah,
You
yeah.
just
Yeah, I'll describe the algorithm once properly. But are there any other ideas that any of you have thought of? Okay.
Excuse me.
Yes, yes.
Ma'am, like, can you just repeat like the part of the question that you wanted to ask? Ma'am, like I didn't really understand it properly.
Okay. So you're with me on the first thing, right? If you want to optimize on time, you needed login jars. And
Yes.
yeah, and this part also, right? If I give you only one jar, then this is the amount of time you end up spending. So the question is, what happens all the way from one jar to log n jars, right? There are so many values in between, 2, 3, 4, and so on. So if I give you, for example, 5 jars, would you be able to come up with an algorithm that is much better than order n? So by that I mean it's not something like n over 2 or n over, not a constant fraction better than previous. I want like really large improvement. So could be like square root n, quadratic or cubic, or I mean n to the 1 over 3 or something.
Okay, got it.
Okay, so let's look at the algorithm that was mentioned. So let's say we are dealing with k equals 2 case. So what he says is, you have this ladder, and what we're going to do is we're going to partition them into, let's say, p many. So this is a p sized sub ladder, this is again a p sized sub ladder, so and so on. Okay, so in the previous case, okay, let me ask this. So if I divide it into p size each, how many how many partitions have we made?
What is the size of the partition?
No, just assume p be any
N by
integer,
P.
n by p, exactly. So you have made n over p partitions of size p each. Okay, then yeah, so then what we'll do is the algorithm is as follows. What the algorithm does is, mm, hmm. Okay, so maybe I'll give you a smaller question. So let's say I have one jar, so totally I have two jars. Let's say this is jar 1 and this is jar 2. Okay, now first I give you one jar, and your goal is to find out in what partition it lies. So maybe the correct answer is here, here, or somewhere. Okay, it's in only one place. So your job is to find out what the correct partition is, and you are allowed to break one jar. So what will you do?
One by one. We'll go from the bottom.
Bottom, or
We have only one jar, right?
okay, yeah. So what you will do is you use the previous idea of um, linear search, and you start here and throw it and see whether it breaks. Then you throw it here, 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 at all, I mean until it breaks. So once it breaks, you would know that your answer lies somewhere here. So let's say that the jar breaks here. So the idea is that, so maybe I'll call this n1, n2, n3, all the way. This is not a good notation. A1, a2, all the way up to a n over p. Okay, so throw the jar starting from linearly at a1, a2, all the way up to a n over p, and stop when it breaks. So suppose it breaks at aj, then what do you know, what do you know, your answer should lie between, suppose it broke here and this was aj, then your answer should lie between aj and aj minus 1. Is that fine? So then you know that your answer lies between aj and aj minus 1. So is this fine with, okay, so now you know your answer lies here, and you have one more jar left. So one of these you have broken, and the other is with you. So then what would you do now?
Again, linear within that.
Exactly. So now you are again forced to do linear because you only have one jar, so you can't do anything better. So now again you do linear search from aj minus 1 to aj, and suppose it breaks at ak, then output ak. So is the algorithm fine? I'll just quickly repeat. So what we did is we partitioned it into size of p. There are n over p partitions. We threw the jars at the boundaries of this partition so that we know in which partition the correct answer lies. Then you again linearly keep on throwing all the way until you break it for the first time. So what is the running time of this, or by running time I mean how many steps did we make in the worst case?
Shouldn't it be n again?
And so let's break it step by step. In the first part, how many times did I throw? At max n over p.
Log n. Oh, yeah, I know.
Okay, so in the first part we ended up throwing n over p times, and in the second part how many times did we ended up throwing at max? P. So the total complexity is n over p plus p. So like yeah, I think like Suyog was asking whether square root 10 or log n, I don't remember what you said.
Log n. Yeah,
Log n.
log n.
Yeah, so what is the correct what is the most optimal thing? So in this case, if I want to optimize, as in I want to minimize this quantity, then what is the value of p that I should choose? Okay, if p is 1,
1.
if p is 1, then you get n plus 1, right? Then you are doing linear time. Whereas let's say if like Suyog said, if you do log n, then you are doing n over log n plus log n, which is better, no? So is that making sense? So okay, so let me go over it again. So what we are saying is you have n over p plus p, and the question is choose the value of p that minimizes the sum. Okay, so let's say you take p as 1, then what do you get? You get n plus 1, right? And let's say on the extreme end, if I take p to be n itself, then again what I get is n over n plus n, which is again n plus 1. Okay, so this is what is happening at the two extreme ends. But let's say I take p equals 2, then what do I get? I get n over 2 plus 2. So between n plus 1 and n over 2, which is better?
N by 2.
Yeah, n over 2. And then again if I make it it's, let's say I make it log n, then what do you get? N over log n plus log n. So again, which is better?
Yes, log n.
Log n, right? So the question
Yes.
is what?
Square root of n is best.
Exactly. So what happens is if you choose p to be very small, which is here, you end up getting uh, a very large number because of this is still very large if p is small, and if you take p to be very large, then this part is small, but because p is large, this is the factor that is overpowering. So that's why you again ended up getting very bad number. But if you keep on if you move from 1 towards a larger number, or if you move from n towards a smaller number, then you will start to notice that you're getting smaller and you're getting better and better values. So where do we hit the optimal? You hit the optimal when p is equal to square root n. So what happens is n over p plus p becomes n over square root n plus square root n, which is 2 times square root n, which is the best that you can do. Okay, so you can use different methods to get the minima, and you can do the derivative thing to get the answer. But yeah, but intuitively, what's happening here is, on one hand, p is, if you increase p, this part, uh, I mean, dominates, and if you decrease it, this part dominates. So you want to uh, hit like a sweet spot where both the quantities will be minimized and nobody dominates the other. Okay, so is this fine? So is k equals to k is fine?
Ma'am, mathematically, I can say, I mean, I find it good, but the thing is, I'm still not able to be, I mean, I'm not convinced that in worst case, it should take anything less than n. I mean, even though we are partitioning and then we are making such thing, but I'm still not sure why are we getting this value.
Okay, so um, okay, so the only way I can think of um, convincing is um,
I mean, it's easier if we take smaller cases. For example, if we take
Uh,
only
See, I
n.
can, I am able to understand this mathematically. I can at least make it at least make sense that this mathematical expression works. I'm not anything. I don't have anything against it, but still, I'm thinking that if we are going to through entire partition, all partitions, and in worst case, what can be, be a possibility that I go to the last partition, then within that last partition, I go to the last element, and
hmm.
I've still not used any binary search over here. I'm still using that linear search only. So in worst case, shouldn't it be n?
um, so in the worst case, what's happening is so um, I would say it's not exactly like binary search because you're not like doing it half half, but um, the idea is that you are dividing your problem into smaller problems, right? So like you said, right, the worst case would be that that you go through the, I mean, the levels that
I
we
mean,
marked.
ma'am, as you have told that we only have two jars. So when you say two jars means I can use one at a time.
No, you
That's
can
what my problem is.
I mean,
When
you
you
can.
say a partition and you are using that one entire partition for a jar, then within that jar I have to go sequentially. No, I don't have any other option, no, ma'am.
Yeah, you can use two jars at once. I mean, that's not a problem, but there's no point in doing that. No, you, at any point of time you're going to stand at one place only, so you won't drop both the jars at once. I mean, so I mean
Ma'am, if I'm not mistaken, I mean, like, let's say jar one and jar two, let's say in proper sense, I think them jar one and jar two as memory locations or memory bulk of memories which I have. Now I am taking partition one and storing it in the first memory location or I mean, whatever address I have. Now I'm using that partition to then within that partition I'm searching for that whatever thing I want to search for. Is this the thing happening, ma'am, or I'm wrong, ma'am?
no, I think the analogy seems fine to me, but yeah, I mean, I from what I understand, your confusion is just that I mean, is just that it's not intuitive why this should work better. That's all, right?
No, I am not able to relate it how I mean in reality it works. Mathematically it works. I can understand it, but how in reality it maps to the real thing which I am going to perform. Let's say a simple search. In binary search, we know that we are splitting the array into two halves and then performing, then again iteratively doing the same thing till we get the that particular element. But over here, we are rather than going for binary, we are making I mean some n by p partitions, and then sorry p partitions, and then within those partitions we are going and searching. then how come we are not getting that entire thing as n? That's what my problem is.
We are skipping, no. Like
Skipping what?
suppose let there are 100 steps and we have
Okay,
2 eggs. So according to our formula, it should come, P should be 10, right?
okay,
Right. So
then
10th level, say on 10th level, you'll throw the egg or the jar,
okay.
whatever. Then
Mm-hmm.
if it breaks, you go from 1 to 10
So
because you
within
have
that,
only one.
so
Yeah, that is
within that
10th.
partition,
Yeah, you have to.
what are you performing? That's what my
Linear,
question.
linear, linear.
Correct. So you did linear for partition one, correct?
Yes, yes.
Then similarly for partition two till
No, 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 no.
partition
If it breaks,
no
if it
it
does not break, if it does not break on level 1, then I will
hmm,
go on level 20. From level 10, I will go to level 20. And if it breaks, then I will go from level 10 to 20. I have to do only 10 at max. I don't have to do 20.
at
And
every level you have to do 10 now. That's what my
yeah,
question is.
10 P in case.
So
That
in
is
worst
why,
case, in
yeah,
worst case, where will you go?
worst case is actually
You'll scan
90th.
yeah you'll scan through entire thing now. So
No,
didn't it
how are you scanning everything? You're taking it into partition. So you will go from, you suppose you go from 10,
okay?
20.
Yeah, that's what my question is. When you say you are in partition one, within that partition you were going linearly.
No, no, we are
No.
not going linearly. We are skipping those 10.
Oh,
Okay,
We are
let's
directly taking on 10.
yeah, let's take the example that Suyog was mentioning. So I think you have 100, right? So you have this 100, 90, 80, and all the way 10. And yeah, maybe your answer is located somewhere here. Maybe it's on the.
ma'am, if we are going to do, ma'am, I get the point, ma'am. If we are going to do 10 comparisons at a time, then it is not an issue. Then everything is fine. Whatever calculation you did is I mean, understood by me. But I thought it was doing one by one. That's where that's where the problem lied with me. I mean, you are taking, let's say, within this example only, from 90 to 100, let's say we are having 10 elements, and we are taking all 10 elements and then comparing. That's what we are trying to do over here.
You're only you're only for the first thing you're doing is you're only checking the boundaries, that is at 10, at 20,
Correct.
all the way up to 100. So you're not checking anything in between, all of that is going to be skipped. So how many comparisons we did at most 10 comparisons, in this case
Correct.
it's
Correct.
9. Okay, so only 9 comparisons we did so far. And now
Yes.
there are only 10 elements here, right? So
Correct.
what you're doing is you start at 80, then start 80, 81, 82, and
Got it, ma'am. Got it, ma'am. Ma'am, this entire thing, I just forgot, ma'am. I got your point, ma'am. Actually, we were coming from binary search and the array was sorted itself. Yes, my mistake, ma'am.
okay, okay, yeah, okay, yeah. Thanks, Suyog and Ravi. Okay, okay. So is this fine for all now? Okay. So then, okay, how much time do we have? It's 7:30. Okay. So, okay. So let's say, maybe I'll just pose it for you. If you can think of this right now, it's fine. Otherwise, if you want to think about it later, that's also fine. So, let us get back to the table that we had. So, so if you have two jars, then you did order square root n. So now the natural question would be that, if I give you three jars, can you do asymptotically better than square root n? So by that, again, we don't mean square root n over 2 or something, but something like n to the 1 over 4 or something. So in general, you can ask, if I have k jars, can you always do asymptotically better than k minus 1? So you can think about this, and the answer is yes. You actually have to use similar idea, slightly modified, to get better than this. So you can try this out. If you have any ideas upfront, maybe we can discuss that. Otherwise, you can take your time and think about this. But is the question clear? Okay, so yeah, so you have, if you have any ideas, you can speak up or you can write in the chat.
I mean, this is like breaking into partition, and then we have one more chance, right, for number 3. So we can use binary search, like we can attempt at the middle point of that. That's the idea I have. Like using the same, trying to divide it into smaller partitions, and we have one more chance. If we break our jar, we can test at a middle point of the partition, and if it breaks, then that, like getting one more level deeper into that. That's the idea. I don't know if it's if there is a better idea.
So so one problem with that is, so if you let's say the partition size is some p for you after using 2 jars, and you know the answer is in that partition. Now if you do binary search, you will end up using at least at most log of p many jars, right?
Right.
So that many you may not have. So for example, if it's 3, if I just give you 3 jars and you already used up 2, now you only
No,
have one.
no. We only try at the middle. If it breaks, then we again do linear till then.
Oh, you are saying that first we'll do binary and get it to n over 2,
Yeah.
and then do,
No.
so,
Yeah. No,
and
I
then do
mean,
the partition,
not. Yeah.
and then do the linear thing, no? So
Yeah.
then the problem is that you used 1 jar and reduced your size to n over 2. Okay, and then what will happen to the, according to our algorithm, it will be n over 2
Not. I mean. Oh yeah. Okay. Okay.
plus
Yeah.
p.
Okay.
So again, if you try to minimize this, you will again still get like order square root n only. It's only
Right.
fractionally better. But what you can think about it, but I'll just give you the idea. If it makes sense, it's okay. Otherwise, you can try it on your own. So the idea is that you do repeated partitioning. So you're going to partition this.
Yeah.
Uh,
Okay. I got the idea. I got the
yeah.
idea.
Once you get that partition, you're going to further partition it, and within the partition, you're going to do a linear. So keep on partitioning only at the end when you have 1 jar left. Only then you, I mean, uh, do the whole linear thing. So that's going to be the idea, and the point is to analyze that it's going to do better than, it's strictly going to do better than the previous, the case when you have lesser number of jars. So that's what I would like you to try. You basically write the algorithm and come up with your running time in terms of this, and try to see what parameters would minimize the number of operations. And then yeah, so the analysis is the interesting part. So you can take this up, and if you would like to discuss this, then let me know. In the next tutorial, let me know. And yeah, okay. So yeah, if there are no questions, if there are no further questions, then now we can move to um the next question. Okay, so I'm assuming, okay, good. Okay. So yeah, maybe take your time and read out this question. um, okay, so maybe I'll just um, okay, So what's happening is that there are students who are seated in the order of. Okay, yeah. So yeah, I think the answer is that, yeah, some of you are already answering. That is correct, but I'll just explain the algorithm. Okay, so okay, so you have this n many students who are seated according to their roll number. So let's say um, this is the order. This is the ascending order of the roll numbers, and then they have some grades that are given to them. So let's say um, this guy has 90, then 87, and then some person R5 also has 90 marks, and so marks can repeat, of course, and then you have say 77 and so on. So these people have some grades, some marks that are given to them, and now what we want to do is we want to sort them according to marks. So maybe the person with highest marks should maybe, let's say R8 has 100, then I would want R8 to be here. But but if there are ties, so if R1 and say R5 here, they have the same marks, then I want R1 to be before R5. I don't want R5 before R1. So I want to preserve this order. Although we are arranging in terms of grades, we'll preserve the roll number whenever there are ties. So this kind of sorting that we do, so essentially we are sorting on marks. Initially this is sorted on roll number, and now we are sorting on marks. So what we want to do is we want to preserve the roll number although we are sorting on marks. So this kind of these kind of sorting algorithms are called stable sorting. So you don't need to come up with like a brand new algorithm. You can just tell me if any of the algorithms that you have seen are stable, and if so, then a reasoning why they are. Okay, so there's bubble sort. So okay, so how many think it's stable? Okay, so if yeah, if you think bubble sort is stable, do you have a reasoning for why it is?
Ma'am, always adjacent two elements are compared, so the order will always be preserved.
Exactly. So what happens is yeah, at some point whenever you're going to keep on swapping, and at some point whenever it so happens that you are comparing R1 and R5, let's say, then you are not going to swap. You're going to preserve this order and continue the idea. So at every point you are ensuring that if at all uh, you are comparing and swapping, then you are preserving the order. Okay, so bubble sort is indeed stable. So what about insertion sort?
It is also stable, ma'am.
Okay, so why is that?
Ma'am, in insertion store, we pick the element and we try to place it inside the container which we have. And for that, we start looking from the end of the container till that time we reach a point that the element is smaller than it. So if sorry, yeah, till the element is, let's say, how to say, in insertion sort, we take an element and we say that it is sorted. Then from the unsorted part, we take another element and then we compare with this element, and if it is found to be smaller than this, we'll place it before that array, in the array, and then we, or else we'll place it after that element. So in this way, if we find that any element is not smaller than it, then we'll always place it after it.
Yeah, that is correct. So what you're saying is in insertion sort, uh, you develop your solution part by part. So at some point, let's say this is the part that you've sorted so far. There's a new element. Let's say there was some R5 with 90 marks, and then there was um, let's say now you the new person that you are looking at is R7, and he also has 90, or she also has 90 marks. Then what we are doing in insertion sort is we are comparing with 97, 99, and then you have 85 and so on. So what you're doing is you're comparing with the elements that you have here and trying to find the correct place for it. So when you do that, when you hit, if if 90 were not originally here, of course you would put R7 here, but now that it's here, you will always find the last you'll always keep it next to the last repeated occurrence that you had. So 90 would sort of come over here, so you are preserving the order. So yeah, so that's why it is stable. And what about selection sort?
We search for the smallest element and then we place it in at the first position. Then in the second round, we again search for the next, the smallest again, and then we place it behind this smallest element. So I think it should also be stable.
Okay, so does anybody disagree with that? Do you have a counter example where okay, yeah, exactly. So like one of you pointed in the comments, what selection does is it finds the minimum element and swaps it uh, with the correct place that it should belong to. But when you swap, it does not preserve the order. It can it can disturb the ordering that you have. So for example, um, if you have maybe this part is already sorted, and you have maybe 100 for some person, okay, I'm not writing this, but you have 97 and then 87 and so on, and the next element, sorry, so this is not correct. So okay, so maybe let's say 10 is the minimum. mm, yeah, and this is R1 who has 90, then there is some person R5 who also has 90, and let's say R7 also has 90. So then 100 is the maximum number of marks. I'm sorting in the reverse order, that the maximum marks to minimum marks. So what my algorithm will do is it will find out this person, say R11, who has maximum marks, and it will swap it with the first element. So then you have 100 here for R11, and this is still R5 90, R7 90, but R1 who has 90 is now here, and so it has disturbed the ordering that you wanted to maintain. People with same marks should have been in the order of their roll numbers. So, and it will keep on disturbing like as it passes through. So yeah, so that was the catch. That selection basically just takes two elements and swaps it, and it does not like sort of push and insert. Okay, so selection is not stable. How about merge?
I mean,
It
merge
should be
sort,
stable.
yeah, it depends on left and right. So in this case, we are going from by roll number wise, so I think it will be stable.
Yeah, so so while you are doing the merging part, so assume that your sub problems can be stably sorted. Then while you are doing the merging, you can carefully do it and let's say you have ties, so from the left part you have same marks and right part you have same marks, then while merging you can make sure that the element from the right part always comes after the element of the left part. So you can make sure that you can implement it in a way that merge sort is stable. So finally, what about quick sort? Okay, so quick sort is not stable. So can you can you come up with a counter example or a reasoning, maybe counter example like this, or any reasoning why it is not?
Ma'am, in quicksort also it swaps the elements, ma'am.
Yeah, so yeah, that I mean the idea is correct. You can try to come up with an example like this and see and show that explicitly it fails to maintain that stable order thing. So so I'll let you come up with that. So the implementation, the algorithm that you have seen where you do the partitioning and put one element in its correct place and then keep on repeating, so the typical quicksort that you see is not stable as it is, but you can make it stable by doing something which is not what we'll get into. So that's not the point of this exercise. So yeah so whatever we discussed so far, is that clear, or are there any questions? Okay, so I think it's almost 8 o'clock. We have I just had one more question. So maybe you can try this out by yourself. So I'll just define the problem. So let's say we have this array of numbers. You have 3 1. So this is an array of size 5, and what we are going to do is we are going to define what is called inversion number of the given of the given array. So what we'll do is for now just let me index this with 1. I'm not getting into the programming part, but I'll just index this like from 1 to 5 right now. Okay, so what we'll do is we will look at all possible index pairs where I can take value from I not equal to 0. So that means I'm looking at all possible index pairs, that is 1 comma 2, 1 comma 3, all the way 1 comma 5, then 2 3, 2 4, 2 5, like that, and finally 4 5. You have 3 4, 3 5, like that. So these are all possible I comma j pair where order does not matter. 2 comma 3 is same as 3 comma 2 for us, so that's not a problem. So what we're saying is let me look at 1 comma 2 pair. So index of index 1 is smaller than index 2, and the value at index 1, so let me call this a1, is also smaller than that of index 2. So this is not an inversion for me. But let's say I look at the pair 2 3, then I look at the pair 2 3, then a2 is larger than a3, but 2 is smaller than 3. So the indices are the ordering of indices is opposite from the ordering of the values. So this is an inversion. So is that making sense? So for example, can you tell me whether 4 5 is an inversion? The pair 4 5 forms an inversion?
Yes.
Yes. So so that's what we mean by inversion. And the question is, how many inversions are there in this array? So um, you can try to come up with an algorithm by yourself, but you have seen you have seen at least two sorting algorithms that implicitly if you modify it slightly or observe something very small, you will see that that algorithm is, I mean, directly sort of gives you the count of the number of inversions.
Bubble sort and insertion sort.
Okay, so insertion sort is correct. So how do you modify that algorithm to give you the inversions? So the
Uh,
hmm,
Ma'am, whenever we are comparing the from an element from unsorted part to the elements in sorted part,
hmm.
uh, no, ma'am. I
Yeah, yeah,
think
yeah,
I'm
yeah. That is actually correct. So um, okay. So what you're saying is that um, you're assuming that this part of the um, this part of the array is sorted, and maybe let's say I'll do it 2 4 6 9. So this part is sorted, and then you are looking at the index a5. So index 5. So this is 1 2 3 4, and I look at the value here. So let's say that value is 3. So, and there is a, of course there's a larger part of the array that we are building, that we are going to build. So what insertion does, it's going to compare with all these values and put it in the correct position. So um, yeah, so what happens is, you compare these two. Do you see an inversion? Then count it. So here you have an inversion, here you have another inversion, and at this point you stop. So there are two inversions. So why is this um, so I mean, why is this correct is because you had this array where, let's say, initially the numbers were not like this. This is something you got after a few steps, right? And then at 5 you have 3, and then there are other values also. So what happened is, even if you sorted these people, you sorted these based on their values, it does not change the relative ordering with respect to 5. So whatever was smaller with respect to 5 is still smaller now. So it does not matter that you change the orderings of these, because it's still going to be smaller than 5, and it's still going to add up. So that's why every time when you add up a new element, and if you count the inversions with the previous one, you will still preserve the order. And why it does not happen with bubble sort is because bubble sort is going to disrupt the relative ordering. It's going to make like swaps a lot of times. So I mean, you will end up over counting or under counting. So is the insertion part clear? Is why, I mean, how it will give the inversions?
Excuse me.
Yes.
Like this, like when I just had an idea, I'm not sure if it's correct or wrong. Like in this question, like as we have to just like write a program to count the number of inversions, right? So like, can't we just put a condition where like if both the like these condition, like if I is less than g and this one is true, and then like just put a counter to increment kind of thing.
Yes. So you can, of course, you can do that. So that will so what will be the running time of that algorithm?
Uh,
order of n square.
Yeah. So
yes,
you
ma'am.
have,
Yes.
yeah, you have two loops, and that will give you order of n square. Okay, so that is, of course, you can write a program that goes through all ij pairs and see whether they are inversions. Okay, so the reason why we are talking about this is that if you look at you've seen other sorting algorithms also, right? Merge sort, quick sort, and so on. So reason we're talking about this is we want to do better than n square. Of course, if you do selection, it will still give you order n square. It's not doing better. But there is another sorting algorithm that you have seen, which, if you observe closely, you will see that that algorithm also like gives you a number of inversion number by a small observation.
Oh, okay. Yes.
Okay, so yeah, there are a couple of, yeah, there's an answer in the chat, which is that you can do merge sort. So um, Okay, so what you do is maybe I'll use a new page. Okay, maybe you can try to think about it first. So how does merge sort um I mean give you the inversions, and I'll take up your ideas. So
Excuse me.
mm-hmm.
So like, mom, in the before one that you are telling about the insertion sort, so like there, so like first we like compare which is the lesser one, and then we increment the counter together, right? That's how it was done.
First
I'm a
we
little bit confused.
sorry, can you repeat that? What do we do?
I'm like, you know, like while you are using insertion sort for like counting,
Hmm.
like I had a doubt. I'm like, can you please tell like if my understanding is correct? So like we just like compare, like we take one element and like we compare if it's lesser than, then we increment a count, right?
Yeah, the number you are comparing is
Huh,
lesser than the ones in your sorted array, then you increment the count.
huh, okay, yeah.
Yeah.
I'll-
Okay, so um, I'll just give you the idea. You can think about it. Maybe take your time later and think about it. If you still want to discuss this, you can maybe let me know in the next tutorial. So the idea that merge sort, why merge sort would give you the number of inversions is, let's say that this is your array of say 1 to n, and let me just take some numbers for now. So this is 7, 5, 2, 4, 9. Okay, I'll just take a small example. So um, let's say you have 3. So this is 1, 2, 3, 4, 5, 6. Okay, so this is the array that is given to you, and what merge sort would do is it will break it into two smaller parts. You have 7, 5, 2, and then you have 4, 9, 3, and then you are going to recursively solve this. So I'm not going through the steps of the algorithm, but let's say it's going to sort it to this, and it's going to sort it to 3, 4, 9. Okay, so I'm only looking at, so right now I'm not looking at the um, maybe I'll ask a simpler question first, then we will see how the merge sort gives you the number of inversions. Okay, so let's say I give you two sorted arrays. Here you have this array and you have this array. So now I want to count the number of inversions that are there um, across these. So what we mean by that is um yeah, you're going to look at 1 4 1 5 1 6, then 2 5 2 4 2 5 2 6, and 3 4 3 5 3 6. You are not looking at the number of inversions that are inside this array and inside this array. You are only looking at what is across. So then how would you do that?
Maintain two pointers starting at the initial index of the two arrays, and then start comparing. Let's say P is the index for first and Q is the index of second. Then I'll compare Q1 with P1 with Q1, and I'll find that the index are, I mean, they are not inversion pair. Then we go to the next element in the first array, and and, uh, have I missed something?
No, I think that I think the idea is correct. So like it's similar to what you do in the merge sort. So you look at these two. I mean, in the merging process, you look at these two numbers, and yeah, and see whether they form an inversion pair. They don't. So then you
Only one of the pointers will be incremented.
yeah, at a time you're only moving one of the pointers. So then you move this pointer. um, okay,
It's
sorry,
still
no, I
not
think you
an
would,
inversion.
oh no, maybe I'll work this out. Okay, so you are here, then you move it here.
Now it becomes an inversion pair.
Hmm. Yeah, now it becomes an inversion pair. And oh no, 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 sorry, it's the other way around. Wait, so yeah, so you check these two, and there is no inversion. So if there is no inversion, then you move the right marker. So why is that? So now I'll check with 4, sorry,
Okay, to maintain the order.
yeah, to maintain the order. So I'll check with 4 and 2. So it's still not an inversion. Okay, so then
And
I'll,
we should be checking the left one, because if 3 is not, then 4 is also not, because it is sorted already. So we should be moving the left pointer,
mm,
because it is already sorted in ascending order. If 2 and 3 are not
okay,
an
so let's
inversion,
say,
yeah,
you do this, then you get one inversion, which
yes.
is 5 3, then you get 7, sorry, then you move 4, right?
No, I think we first check 5 3. We have 5 4. We don't have 5 9. Then we move to 7. Then we check 7 3 7 4. We don't have 7 9. I think that's a good solution.
Okay, maybe I'll do it slowly. So you're saying, can you repeat this? So you're saying first you do
We start from 2. We check that
2
2
and
and 3 do
3.
not form. Yeah,
Okay.
2 and 3 do not form. So since 2 and 3 do not form, all the elements next to 3 are already greater than 3. So there is no point in checking with 2 again.
Hmm.
So
Okay.
we directly increment the left pointer,
Hmm.
and now we check with 5 till we approach a bigger element, that is 9 here.
Hmm.
So if there were more elements next to 9, there was no point of checking them, because it doesn't form a inversion already. So now we increment the left pointer again
Now you
and
increment
repeat this
5.
process.
Yeah.
But ma'am, 5 3 would be an inversion pair, no? And we have missed it.
Hmm.
5 3 5 4 both will be the inversion pair. We can
We
check
haven't missed it.
basically
Yeah,
to
when we check,
9 before 9.
Yeah.
yeah,
So everything. So the first inversion pair that you got was 5 4, and
yes.
since 5 4 is an inversion pair, 5 3 is also an inversion pair. So
No,
everything.
no. I think whenever
Sorry.
we
4
increment,
5 9 is also.
no,
Sorry.
five
Sorry.
nine
Sorry. Sorry.
is not inversion. I mean, when we increment the left pointer, we set the right pointer to the leftmost index again. That could be done.
It means that, ma'am, when
No.
we
No. No.
select the pointer to the 5, the right pointer should be on the 3. And then we can shift the right pointer to the last
But
element.
I think that is deviating from the way merge sort works.
Yeah. So there is a way to do this without having to reset the pointers back and forth. So it's just one linear pass, and it's very similar to what merging process does. But I think I confused. I think I confused you with some. Okay, so maybe you try this out on your own, and in the next
Yeah,
tutorial we'll start with this.
sure, ma'am.
Okay, and next tutorial will be, so there is a Google form where you can put your preferences for the for the tutorial timings, and we'll go with the majority. Then I'll request them to change the slot. If that is approved, only then we will have different timing. And if at all it changes, you will get to know through the mail. So you get reminders, right? So for today's session also, you might have gotten a reminder by mail.
Yes, yes.
So you will get to know through the mail, if
So
there
we
is
have
a
like one session a week, right?
one session a week, which was supposed to be Fridays 6 to 8, but I think a lot of people had difficulty in the slot or something, so we
Yeah.
decided to take a poll. Okay, so how are the questions today? Were they like on the difficult side, or um, or I mean any feedback that would help design the future questions?
It was a good slope, yeah, moderate, easy to moderate.
Okay, how about others? Okay, you can let me know in the via mail or anything, or yeah, anything is fine. So okay, so then next we'll meet based on how the poll goes.
Ma'am, I had a
Ma'am,
question. Yes,
Okay.
where can we find such questions and like mathematics for more illustration, like the analysis of algorithms? I
Yeah, so
mean,
the
in the lectures, it is not so elaborate. Right now, I'm in week one. I'll be moving to week two, but the mathematical part, like taking differential and log and under root n, the kind of analysis we did.
yeah, I think the two books that I mentioned, Corman and Tardosh, Kleinberg Tardosh, those are the best references you can find for course on algorithms. And there are solved examples also where you will see a lot of mathematical analysis. And there are unsolved ones also which are interesting. Some of these I might have taken from the two, either of the two
Oh, okay,
books.
okay. Thank you.
Okay.
ma'am, I had a small doubt. Ma'am, like I will complete my BTech second year this April month. So can I apply for a internship? Like I have got top 1% in the last July to December NPTEL course. So is it possible for me to apply this year?
Okay, so generally the internships open during summertime. So application starts around like March, April something, and then there's some CGPA criteria through which I don't know. So it goes like that. But if you directly want to approach faculties, you can mail them. You can tell them what is your research back. I mean what courses you have done and what interests you, and you can write to them. Directly, and if they are interested in working or inviting you, then that can work.
Ma'am, so would they provide us a form or something, or we should just mail them and they're going to mail us back?
So these forms are not, I mean, are specific to institute. So the institute releases it. You can find announcements on the institute webpage. And then there is a process that they do. They have some algorithm for selecting students and so on. So based on that, they invite students, but directly also you can write to them. And yeah, the forms, but you'll only get to know a week or two, I guess, before it opens. And the dates are also not like very specific, but it opens somewhere in March, sometime in March. um if yeah, if it does open sometime during our tutorials, I mean while tutorials are running, I'll let you know.
Yeah, sure, ma'am. Thank you, ma'am.
But yeah, keep checking the websites also.
Uh,
Okay, so email I've shared. I'll write it here also, but I've written it on the first page of this notebook, which I'll upload on the drive. So okay, so this is the email ID. You can reach out to me on this. Other than that, if you have any questions that you would like to discuss, you can use the groups also, so students can also participate. So yeah, I mean I would encourage you to use the groups for discussions also. Okay, so I'll stop the recording, and yeah, okay.